Math 162, Chapter 4, Exponential and Log Functions. Exponential functions typically represent growth when food or resources are not limited. Examples include population growth, growth of a bacteria colony, growth of a fetus after conception, growth of money with compound interest. Radioactive decay can also be represented by an exponential function. The inverses of exponential functions are called logarithmic or log functions. Example 1. A certain bacteria population had 4 bacteria at time 0 hours and doubles every hour as long as there's unlimited food supply. A. Express the population as an exponential function of time and sketch the graph. First step, we want to find a formula for the number of bacteria. I'll make a column for time and a column for bacteria. And at time 0, there's 4 bacteria. After 1 hour, the number of bacteria doubles, so it's 4 times 2. After 2 hours, it doubles again, so we have 4 times 2 times 2, which we can write as 4 times 2 to the second power. After 3 hours, it doubles again, so the number of bacteria 4 times 2 times 2 times 2, which we can write as 4 times 2 to the third power. Okay, so it looks like we notice a little bit of a pattern here. We have time 2 and we have exponent 2, time 3 and we have exponent 3. We can also write these other expressions using exponents. 2 is the same as 2 to the first power, so we can write this as 2 times 2 to the first power. And 4 is the same as 4 times 1, and 1 we can write as 2 to the 0 power. Any number to the 0 power is 1. So now we can maybe see the pattern. At time 0, we have exponent 0. At time 1, exponent 1. Time 2, exponent 2. Time 3, exponent 3. So the formula for the number of bacteria is going to be 4 times 2 to the t power. So B is equal to 4 times 2 to the t power. And now that we have the formula, we can use that formula to compute values for other values of B for other values of T. So we want to make a table and table of values, and I'm going to use smaller values because some of these numbers are getting to be pretty big. So for purpose of graphing, I'm going to pick some smaller numbers for T. So T is time, and B is the number of bacteria, function of time. Okay, so I'm going to start with time -2, just because it's going to be easier to graph with smaller numbers. So if we go backwards in time 2 hours, number of bacteria is 4 times 2 to the -2 power. Negative exponent means 1 over the positive exponent, so it's 1 over 2 to the positive 2 power. 2 to the second power, 2 times 2 is 4, so this is 4 times 1/4, and this will be 4/4, which is going to be 1. So if we go back 2 hours in time, there was only 1 bacteria, assuming the same pattern of growth occurred. If we go back 1 hour, T is -1. Number of bacteria 4 times 2 to the -1 power. Again, we can use the rules for negative exponents to write this as a fraction. 4 times 1 over 2 to the first power. So this is 4 over 2, which is equal to 2 bacteria. Times 0. 4 times 2 to the 0 power. Any number to the 0 power is 1, so it's 4 times 1, which would be 4 bacteria. After 1 hour, 4 times 2 to the first power, 4 times 2 would be 8. And after 2 hours, we have 4 times 2 to the second power, and this will be 4 times 4 to the second power is 4, which is 16. Okay, so now we can make a graph, use these to plot some points, We have to go, we want to go, in order to plot all the points, we have to go up to at least 16. I'm going to go up to 20. And then the number of hours, we just need to go left or right 2. We could go further. Okay, so then, so I drew the coordinate, do the scales. I made the scales to fit on the page, so I scaled the T differently than the B because the numbers were bigger for the B scale. So I just scaled it to fit on the page. Okay, so then we can plot the points. So if we go backwards in time 2 hours, we have 1 bacteria. So go 2 to the left, up 1 when we plot that point. And then it's 1 to the left, up 2. 0 left to right, up 4. And 1 to the right, up 8. And then 2 to the right, up 16. And then we can connect the dots, and that's going to be our graph. That's called an exponential function, base 2. Okay, okay, so one thing to notice about this graph is that it's invertible. At part B, we want to sketch the graph of the inverse function, but we first want to check to make sure that this function is actually invertible. And it is invertible because it passes the horizontal line test. So whenever we draw a horizontal line, it only touches the graph in one spot, or at most one spot. So it passes the horizontal line test, so that means there is an inverse. And so in part B, we want to actually find the inverse. So part B, we've already done the first step. It passes the horizontal line test, so there is an inverse. And to get the formula for inverse, we want to first start with the formula for the original function, b equals 4 times 2 to the t power, and solve this for t. So we want to isolate the t. We want to do the operations in reverse order. Normally, normal order of operations is exponents before multiplication, but when we're solving an equation, we want to reverse that. Work with the multiplication before you work with the exponents. And to get rid of this 4 here, which is part of a multiplication, we can divide both sides of the equation by 4. So divide both sides by 4, and on the right side the 4's will cancel, and that'll give us b over 4 is equal to 2 to the t power. Now there's no algebraic way of solving this for t, to isolate the t here. But we know that there is an inverse function, and we're just going to say, we're going to call that inverse function log base 2. So what we want to do is take log base 2 of both sides. That's going to be the log inverse function of exponent base 2 function. Take log base 2 of both sides, and on the right side, the log base 2 and exponent base 2 will cancel, because the way we define log base 2 is that it's the inverse of exponent base 2. So those cancel, and that isolates the t. So now we've solved the equation. We have log base 2 of b over 4 is equal to t. And it's usually it's traditional to, when you're solving an equation, to put the letter that you're is by itself, to put that on the left side. So we can write this as t is equal to log base 2 of b over 4. Okay, so now we have a formula for the inverse function, and we can use that to plot some points and sketch the graph. Okay. So okay, so let's make a table of values, and so I'm going to put b on the left now because we're switching the inputs and outputs, and t is equal to log base 2 of b over 4. And for convenience, I'll just use these same numbers that I used before. I have these, my outputs before were 1, 2, 4, 8, and 16. So I'll use those same numbers for inputs now because we're just switching the roles of B and T. And so I'll start with 1. If there's 1 bacteria, then the time is going to be log base 2 of 1 over 4. And we want to write this in exponent form. It's log base 2 of 1 over 2 to the second power. And we can express that with negative exponents. This is log base 2 of 2 to the negative 2 power. Log base 2 and exponent base 2 will cancel. And that just gives us negative 2. And then the next number I want to put in is 2. The 2 bacteria. The time is log base 2 of 2 over 4. 2/4 reduces to 1/2. Log base 2 of 1 over 2. We can express this with exponents again. This is 2 to the negative 1 power. And again, log base 2 and exponent base 2 cancel, and that just gives us negative 1. And then when B is 4 bacteria, the time is going to be log base 2 of 4 over 4. 4/4 reduces to 1, log base 2 of 1. 1 is 2 to the 0 power. Any number to the 0 power is 1. And log base 2 and exponent base 2 cancel, and that gives us 0. And 8 bacteria, the time is going to be log base 2 of 8 over 4. 8/4 reduces to 2, log base 2 of 2. We can write this in exponent form, log base 2 of 2 to the first power. Log base 2 and exponent base 2 cancel, and that just is equal to 1. And 16 bacteria, the time is log base 2 of 16 over 4. 16/4 reduces to 4. We can write this in exponent form, log base 2 of 2 to the second power. Log base 2 and exponent base 2 cancel, and that just gives us 2. Okay, so now we have some values, and we can plot the points. Okay. So now we're before the original function, b was the vertical scale. Now it's going to be the horizontal scale. And time originally was the horizontal scale. Now it's going to be the vertical scale. Okay, so then we can plot the points. So when there's 1 bacteria, the time is negative 2. So that's 1 to the right, down 2. When there's 2 bacteria, the time is negative 1. That's 2 to the right, down 1. When there's 4 bacteria, the time is 0. 4 to the right, up or down 0. When there's 8 bacteria, the time is 1. That's 8 to the right, up 1. And when there's 16 bacteria, the time is 2. So it's 16 to the right, up 2. And connect the dots. and that's our function. Okay, so some things to notice about these graphs. Both of the functions are increasing. They go up as you go from left to right. Here's the log function. Here's the exponential function. They're both increasing. The domain and the range switch. It's another thing to notice. The domain for the original function was all real numbers, and the range was only the positive numbers, and that switched for the inverse function. Now, for the inverse function, the domain is the positive numbers, and the range is all real numbers. Also, the asymptote switched. Asymptote is where the number of bacteria is 0, and that's the same for both functions. But for the original function, the asymptote was horizontal. The number of bacteria being 0 is a horizontal asymptote, but this curve gets closer and closer to 0. Whereas it's still where b is equal to 0, but now it's a vertical asymptote. Another thing to notice is that although both functions are increasing, the original function starts out increasing very slowly, and then it becomes very steep after a while. Whereas the log function or the inverse function starts out increasing very quickly, and then it kind of levels out a little bit. It's still increasing, but not as fast. And that concludes this presentation.